All right, everybody is here. So, should we get started? I don't know, 30 seconds early? Yeah, okay. Good morning, everyone. Hello, welcome to your one day of class this week. That's just how the schedule happens, you know, you do. All right, so we're gonna try to pack everything into one day. But of course, as always, if you need more time with something, let me know. If you have more questions with something, let me know. Send me an email. I'm happy to give you more time, help you out, answer questions anytime. Okay? So don't feel like suddenly there's more pressure. But it's time to get down to business. We've got some work to do. Okay? We can't take the whole week off. As nice as that sounds. We've got to deal with, what are we dealing with? Where are we? Right? Algebra 2, we are in 9.6. Oh, we're so close. We're almost done, right? Rationals, rational functions, rational equations, rational expressions, all that in there. And then remember last week, we threw in a couple of, hey, here's some like other types of general types of relationships, identifying things. You all made some excellent matching games on there. That was really well done with that. So now we're going to get back to the big old rationals themselves, except now instead of graphing, we are solving. Okay? Instead of graphing the functions, we're just solving the equation. Good old straightforward, just run the algebra, crunch the numbers. Okay? And this is what we do if, let me go down to the examples first, just to give you a preview, right? What we're dealing with. We're still just solving an equation, like you do, okay? Except what makes this unique is that we've got stuff in denominators, okay? In fact, this is, we'll start here with the easy one, just kind of reminder of how does this work? Wait, what do we do with denominators again? Okay. If they're just basic fractions, it's not really a big issue, okay? We can't add these together as is. We need a common denominator. So we're going to try to find the least common, the smallest possible common denominator. Find the least common multiple of, in this case, 3 and 2. That would be the first common multiple, just 6, right? Multiply them together. Okay, so to get this to be 6, we got to multiply by 2 over 2. That way, within this fraction multiplication, 2 times 3 gives us 6, right? And then up here, we'll have 2 times 2x, and so we'll get 4x. Over here, we'll multiply by a different foo to get a 6. This one will be 3 over 3, right? So 2 times 3 makes 6, and now 3 times x makes 3x. And so now we have 4x plus 3x. We can combine those into one fraction because they have the same denominator, 6. And 4x plus 3x equals 7x. So 7x over 6 is equal to 5 over 6. Aha! Right? Now it's trivial. Now we just multiply both sides by 6, which basically means eliminate that, right? Multiply the whole equation by 6 to get rid of that. And now 7x equals 5. So divide both sides by 7, and x, right, that reduces, equals 5/7, right? You've done something like that before. Any questions there? Because this is the key. This is the basis from which we further expand it. What we're going to do next, if you see it, is now we're going to start sticking the variables in the denominator, right? The very thing that screwed up the wonderful rational graph. In fact, actually the first rational graph, the parent function of a rational function, right, 1 over x, has the variable in the denominator, right? Which means there's a point at which we're not allowed to equal that number. Okay, you can't do that. You can't have the denominator equal 0. That's never allowed. You end up with vertical asymptotes. Okay, so that's going to play a role. It's going to start screwing things up. But overall, here is our 4-step process. So what we're going to need to do first is check for those excluded values. Where will the denominator potentially equal 0 if we were to allow it, which we will never do. So we're going to make a list of all the x's such that the denominator would equal 0, and then never let x equal those numbers. Okay, that's the first step, right? They might show up later as extraneous solutions. Okay? In the process of actually solving, we might end up with that number. Say our excluded value is x equals 2. And then we go and we actually solve the thing. We say, hey, x should be either 2 or 3. Wait a minute, but we excluded 2. So that means cross it off the list. It's an extraneous solution. It looks like a solution, but it's a trick, it's a trap. It's not really there. It's extraneous. Okay? If it's on the excluded value list, it's not a real solution. So that's why we get that list first. Then you go through basically the same methods as we did with just the normal fractions, right? Find that least common multiple of the denominators, multiply both sides by such least common multiple, okay? And do all the distribution, right? Watch out for those subtractions. Just because you got that negative sign, make sure you distribute the negative, okay? If subtraction is involved, make sure you distribute the negative. Somebody's going to mess that up at some point. It happens to me all the time. Okay, this is why we have multiple practices. Okay, so you get used to it. Get the mistakes out of the way first, so you don't have them on the test, right? And then finally, reduce, simplify, solve. Right? After you've done that, now you're just back into, hey, this just looks like a regular equation, right? Combine like terms, simplify, all that stuff, right? The regular Algebra 1 level solving ensues from there. You could be looking at a linear equation. You could have quadratic or some other higher polynomial. It's possible. So use those techniques as they apply, right? Once you get rid of the rational, if whatever's left is quadratic, solve it via you would any other quadratic. Okay? And now it's very important here that you do check your work. This is one of those times where it's not like, I'm not sure, did I get it right? Let me double check and just plug it back in just to see that I didn't screw something up. This is like actually necessary. You need to double check the answers that you think you got, okay, against your list of excluded values, because you're not allowed to have any of those. If you said exclude x equals 2, we're not allowed to equal 2 because the denominator would be 0. I can't divide by 0. Okay? And then you tell me your answer to the equation is, the solutions are x equals 2 and 3. I've got to take off points. You even told me it's not supposed to equal 2, and then you told me it's supposed to equal 2. Make up your mind, right? You've got a contradiction there. We can't have that. So you got to make sure all your solutions, okay, your final answer, when you do the work and you find x could be 2 or 3, take one next step and write down, okay, in a box, the solutions are actually x equals 2. Box that. Not 2, sorry, 3, I suppose. Okay? And only that. Don't include the rest. Anything that you call a solution has to work in the original equation, the one with all the rational stuff, the one that's dividing by stuff, okay? Not the one that you've manipulated. Yes, technically your manipulations are valid, but they will yield a different function with different, possibly different solutions. We're only looking for which ones are the same. Make sense? Okay. Let's look at some actual examples. This will help clear things up. All right, here we go. We'll start simple here. Rational expression on one side, we've got some rational on the other. We need, first and foremost, we need common denominator here, so we can combine this, right? So let's do that. To start with, this is not just 2, it needs to be 2 times 2x over 2x, right? So that's what I have over here, which means this gives me 4x. So now I have 4x minus 5 all over 2x. Okay? And equals 2x over x plus 1. Now it's just a simple proportion, right? It's two ratios. This over this equals that over that. We know what to do with that. Okay? We can multiply by the least common multiple. Really, we're going to multiply the entire equation by all of the factors that appear in the denominator. So we're going to multiply it by an x plus 1 and a 2x. Okay? So that on this side, when we multiply by x plus 1, well, that cancels out with that guy, right? And we don't have to deal with that. Instead, we just have 2x times the 2x over here. And on this side, when we multiply by the 2x, that's going to cancel out with this part of the denominator. And we only have to deal with the x plus 1 times this. Which means, oh, looks like we are distributing here. So let's quick, 4x times x is 4x squared. 4x times 1, 4x, minus 5x, minus 5. Okay, combine like terms there. 4x squared minus x minus 5, and 2x times 2x is 4x squared. Now what can we do? We can subtract 4x from both sides. That would leave us with, well, this would be a 0 equals negative x minus 5. So let's add 5 to both sides. Divide by negative 1, so negative 5 equals x. Is that our final answer? Is that actually allowed? Right? We didn't check for extraneous solutions. What are we not allowed to equal? Take a look at this denominator. Okay. X cannot equal 0. So that would make 0 down here. Or negative 1. Okay? That's our list of extraneous solutions. Should have done that first, really. It's a better habit to get into. Check that first. Okay, negative 5 is not on our list, so it should work. Let's please double check. Make sure we didn't add anything in, because remember, I was multiplying stuff by x's. Okay? Whenever you multiply the equation by stuff that contains the variable, you have the potential of introducing new extraneous solutions. No, it sounds crazy. I thought we were trying to get rid of the extraneous solutions. It's possible you can recreate new extraneous solutions that weren't there before. And I think we'll see an example of that better in the next one. But keep that in mind. So you always, always, always have to check. Not just your old not allowed values, but check the original. If I put negative 5 in here, will I cause problems? So 2 times negative 5 is negative 10. Negative 5 plus 1 is negative 4. Negative 10 divided by negative 4 is positive 2 point something. Okay, it works. Is that the same as 2 minus 5 divided by 2x? Well, 2 times negative 5 is negative 10. 5 divided by negative 10. Maybe this doesn't work. Does this equal 2 minus 5 over 2 times negative 5? This is negative 10. This is negative 4. And this is negative 10. 5 divided by 10 is 1/2. So it's '2.5. Is 10 divided by 4 2.5? Can because negative divided by negative, that'll be positive. Half of 4 is 2. Oh yeah, it is 2.5. It was 2 point something. I didn't process all the way to get the exact decimal. Now I need it. Okay, 2.5 equals 2.5. Check. Whew. It's true. It works. Negative 5 is our answer. Put the whole thing on screen there. There you go. Any questions there? All right. Example number 3. It's getting much more complicated because now we've got a quadratic within the denominator. Oh boy. Okay. So first up, excluded values. What are we not allowed to equal to? Start there. A should never be set to positive 2 or positive 6 or what about over here? What is this guy? I don't know. That's standard quadratic form. We got to factor this thing, right? When in doubt. Hope it's playing in your minds, even if you're not saying it out loud. Factor it out, okay? When in doubt, factor it out. So, is it a special product? No. Perfect square? No. 12 is not square. Factors of 12 that add to negative 8. This is an invisible 1, so I can go straight to answer format. 2 binomials, each starting with A. Factors of 12, 2 and 6. Ooh, if they were both negative. Negative 2, negative 6, right? Negatives multiply to make positive, add to make further negative. Perfect. Hey, that's the same numbers we had over here, Mr. Apple. This doesn't have any new factors. Ha! Very good, very perceptive. In fact, I would use that as like your prediction. I think I mentioned this actually in the add-subtract rational expressions, right? Predict. Right? It is safe to assume that book problems are more likely to be friendly than unfriendly. Okay? A friendly problem would give it to you, be like, boy, it'd be really convenient if this was actually just these exact same factors. Hey, look at that. They're the exact same factors, right? Check for convenience first. All right, so it's just 2 and 6 we have to worry about, which means now our LCM of the denominator is a minus 2 times a minus 6. It is this whole thing, right? So if we were to multiply this whole equation by, that looks horrible, a minus 2 times a minus 6, right? This entire denominator would cancel out. On this side, remember you have to distribute to everything. So this, this whole factor, that's 1. This item gets both of these. This one gets both of those. So yes, the a minus 2 will reduce, the a minus 6 will reduce. What's left? Up here, instead of a minus 2, the thing left is a minus 6, so I have the a times an a minus 6. In the next term, I have a 1 times a minus 6 reduced. What's left is the a minus 2 factor. And then on this side of the equation, the 4 times both of these factors reduced with that denominator, so it's just the 4. Look at that, huh? Isn't that neat? You multiply by one thing, and you eliminate all of the denominators at the same time. Boom, 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 boom. Different portions. Super cool. It's like setting up a nice set of dominoes. You set them up and knock them all down. Okay, and now it's just algebra 1 stuff, right? Distribute, combine like terms. Okay, a times a is a squared minus 6a plus a minus 2 equals 4. So a squared minus 5a minus 2 equals 4. It's a quadratic. deal with it as you normally would. Move this 4 over a squared minus 5a minus 6 equals 0. Factors of negative 6 that add to negative 5. 1 and 6. Yes, if we made that negative 6 and positive 1, okay, they would multiply to negative 6. And negative 6 plus 1 is negative 5. Aha! That works. That's factored. That equals 0. ZPP, a minus 6 equals 0, or a plus 1 equals 0. So a must be equal to positive 6, or a equals negative 1. Are those my solutions? Is that my final answer? Should I just circle them both and call it done? Spoiler alert, if the teacher ever asks, are we done? The answer is almost universally, no, we're missing something. Check, check, check. Are those answers allowed? A can never be equal to 2 or 6. So we take this a equals 6 and we cross that out and say, no, you are an extraneous solution. Okay? You're a result of taking what was a rational equation, flipping it back into a perfect parabola. In fact, what happened here, if I may whip up a quick graph, right? What we had originally looked something like, I think something like that. Right? And no, because it did have one solution. Hang on. At negative 1, right? So at negative 1, so we have a horizontal asymptote here at not 0, and see, this is why doing the asymptotes first is so much easier. Okay, there was our original. And then we turned it into a parabola, right, that also intersected over here at 6. We don't want that. We only want the negative 1. They both share this negative 1 solution. They did not both share that 6, okay? The parabola gave us an extra that we didn't need. The real only solution is a is equal to negative 1. Okay? Double check. Put that back in the original. Let's see. Check. Negative 1 divided by negative 1 minus 2 plus 1 over negative 1 minus 6 equals 4 divided by negative 1 squared. What was it? Minus 8a. Minus 8 times negative 1 plus 12. Okay, all right, negative 1 minus negative 2 is negative 3, so I have negative 1 divided by negative 3 plus 1 over negative 1 minus 6, negative 7 equals 4 over negative 1 squared is 1 minus 8, that'll be a plus 8 plus 12, right? So 21. That's good because I need to combine thirds and sevenths. So adding fractions, I need common denominator. That's going to be 21 anyways. So this is going to be times 7 over 7 times 3 over 3. So really I have negative over negative. This is positive. So I just have 7 21ths plus this negative, though, stays there. So negative 3 21ths. Equals 4 21sts over 21. 7 minus 3 is 4 over 21 equals 4 over 21. Check. It is correct. It does work in the original equation. Negative 1 is, in fact, our one and only true solution. Questions there? Right, then you have your practice, actually the intervention worksheet for tonight, I believe. That's the one that has the notes on it as well. So there's a few more examples you can always refer back to if you get stuck. Otherwise, you can ask me additional questions. Have at it, get started. That is your homework due Friday morning. Again.